today we're going to be going over question 2 from the spring 2024, so just last year, uh, exam 1. And this is, I'm only going to do part A for this problem because this is quite a long problem. And part A does take up pretty much all of that question, all of this question. So what we're given here is we're given a spherical non-uniform volume charge density that exists in this yellow area right here. Right? I mean, I probably didn't have to highlight it with blue, but you get it. It's in the yellow area. And surrounding the spherical charge region and it is a thin spherical shell of a surface charge density rho, I believe this is rho x, so I'm going to call this rho x0, of radius b. So we're given actually two charge densities at two different locations. It's very important. Surrounding the thin spherical shell of a surface charge density is a PEC shell, spherical shell of inner radius c and outer radius d. The PEC shell is neutral. Okay, so what does it mean for a PEC shell? Because we can get an answer really quick. A perfect electrical conductor shell means it has no charge inside. What does it mean if it has no charge inside? Well, that means there's no electric field inside. Okay, think about Faraday's cage, right? So right away, what we can do is we can say C less than R less than D, the area right here. We can say the electric field from this little part, right, is going to be equal to 0. Okay, I might as well put the units here just to make sure we don't lose any points, but it's going to be equal to 0, right? So this is something I believe in notes 12, if I'm not, it might be in notes 11 also, I believe, for Gauss's law, but anyways, we can get started. Now we know an answer to the first one. Okay, so let's start with R is less than A, just to get kind of like our basis. Well, there has to be an equation that relates the surface charge or the charge density to electric field, and there's going to be one in specific, not necessarily exactly what we want though. The way we're gonna do this is we're gonna do kind of like 2 or 3 steps in between. What do we know? Using Gauss's law, we know that for a spherical shell, this will always be true on the left-hand side. It's going to be dr 4 pi r squared, which is the surface area. And where do we get this equation from? Well, we get this equation from, let me get, right here, the closed surface integral of the flux density vector dotted with its normal vector with respect to ds, surface area. And so what we get is whenever we have this sort of thing, what we can then say for a spherical shell, this is dr 4 pi r squared. And this is the left-hand side, because on the right-hand side, whenever you're using the equation, you can set this equal to the enclosed charge, the charge that is inside of this surface area. Now, how do we get this charge? How do we get this enclosed charge? Well, the way we get this enclosed charge is we use the charge density we're given. So Q enclosed will always be equal to the, whether it's the contour, surface, or volumetric integral of your rho linear surface or volumetric charge density with respect to the linear surface or volume. This will always be true, so you can use this equation every single time. There are some shortcuts later on, which we'll see actually in this problem, but especially for non-uniform charge densities, you have to use this. So for R's, what are we given? We're given a volumetric charge density. So what we're going to be doing is we're going to be using the volume parts of this equation. So we can get rid of everything else here. And now we have this equation. Now we have to figure out, well, what are we going to put for the bounds? Because we have rho v, which is what we're given up here, r cubed. dV is going to be a little bit interesting because, again, if you don't have note 6 in your crib sheet, you won't know this unless you have it memorized. It should be, okay, I know what it is. dV for spherical coordinates is r squared sine theta, dr, d theta, d phi. Notice it does not have a z component, and we're not given a z component, which is very important. Now, rho v depends on r. Now, what are the bounds going to be for our volumetric integral? Remember, a volumetric integral will end up being a triple integral. So we have a triple integral here, and we're going to let the inside integral be r. We're going to let the second one be theta, and we're going to let the outside one be phi. Okay, so r goes from 0 to r, whatever it changes, whatever it wants to be, 0 to r. Now, theta, for spheres will always go from 0 to pi. For phi, this will always go from 0 to 2 pi, unless you have a semicircle or a hemicircle. You have to know the at least the phi values. Theta will most likely always be 0 to pi. Just be careful about it, okay? If you have questions, you can ask, of course, but there are also great notes that he's given for note 6, and it tells you why. I just don't want to lengthen this video showing exactly why that is. So now, rho v, we have r cubed, but remember we're multiplying it by r squared, so let's just call it r to the 5th sine theta dr d theta d phi. And remember, this is all for r is less than a. So we're inside of that yellow circle or yellow sphere. All right. So now, Q enclosed, because this is still the same thing here, what is the integral of r to the 5th with respect to dr? Well, that should be 1/6 r to the 6th, right? So 1/6 r to the 6th, and we'll pull this to the outside. Now, what we can do is, I should have done this at the beginning, but we can now just break it apart. We can break this sort of integral apart into its pieces. And so now we get, what is the integral? What is the integral of d phi? Well, it's just phi, evaluated from 0 to 2 pi is 2 pi. So we have 2 pi over 6 r to the 6th. Integral of sine theta is negative cosine theta, evaluated from 0 to pi. That equals 2. So times 2 is equal to 4 pi over 6 r to the 6th. So now that is our Q, our enclosed charge from R to A. But we're not asked for enclosed charge from R to A. We're asked for the electric field vector. Why did I have us go through this entire process to find the this value here, the flux density vector? Well, through Maxwell's equations, or I guess sort of through Maxwell's equations, we have another equation that relates these two. We have E, the electric field vector, is equal to D, but multiplied by the I believe permittivity of free space, or I don't remember which one it is. It's been a while. Epsilon naught, right? So now what we can say is the electric field vector, which is what we want, is D divided by epsilon naught. So what can we do? We found Q enclosed, and we know, what else do we know? Well, we know dr times 4 pi r squared is equal to Q enclosed by the equation we had set up on top. So what can we do? That means D is equal to 4 pi r to the 6th over 6 times 1 over 4 pi r squared. And we notice what the 4 pi's cancel. R squared goes, this brings it down to 4, so it's equal to r to the 4th over 6. All right, so then we can bring it up here now. So E, the electric field vector from whenever r is less than a, is equal to r to the 4th over 6 epsilon naught. And you cannot forget which way it is propagating. It is in the radial direction, going out, because any charge radiates outwards, right? At least in statics. And what are the units for this? This is volts per meter. So now this is our answer for the first, for when the charge is less than A. That's the electric field vector when R is less than A. Now, what do we do about after? What do we do after it's greater than A? Because now we're doing A is less than R is less than B. So the length that R is between A and B, where is that? We'll highlight that. This is right here. Okay, so now we're outside the sphere. One thing to ask whenever you're doing these types of problems is, has there been an additional charge or charge density introduced into that region? Enclosed in that region, not outside, but enclosed, because that's what it depends on, right? The Q enclosed. For a sphere, this never changes. This is always true. This is the only thing that can change. The enclosed charge is the only thing that can change. So has it changed? Well, no, it hasn't. Because now the only charge enclosed in between A and B is A. Whenever that yellow, light yellow spherical charge. So that means Q enclosed must be the same. There's a caveat to this. Because A is baselined, meaning the charge only gets to length or distance A. That means the A inside of this enclosed, or the R inside of this enclosed charge, which was what? 4 pi 6th R 6th. So we'll write this. This R here, because it cannot get any greater than A, we set it to be A. It does not change the position, the charge position does not change. It is stationary. So we let this be A to the 6th. So now for whenever R is between A and B, we have 4 pi A to the 6th over 6. Now, whenever we do dr, 4 pi R squared, and remember this R does not change. This will always stay R, because this is asking what is the, let me see exactly what the meaning, the flux, what is the flux density vector at a distance R? That will change. We can vary that value, but this charge density does not change. It doesn't change with time. It's stationary. So we let this be equal to 4 pi A to the 6th over 6, and now we can divide it. So we divide it, and what do we get? We get times 1 over 4 pi R squared. Well, this 4 pi still cancels, but now dr is equal to what? A to the 6th over 6R squared. So now A to the 6th will stay stationary, but R will be variable. And now what can we do? Well, we can use this equation again, and we can find the electric field vector when R is between A and B is going to be equal to A to the 6th over 6 epsilon naught R squared, and you cannot forget that it is projecting radially. Again, volts per meter. So now that is how we get our answer for this part. Be very careful, because if you have just R to the 6th always, that's not true. Oops. So hopefully that made sense, and you can replicate this in any of your problems here. The next part, B, whenever R is between B and C. What happens when R is between B and C? So now we're in, I'll highlight the screen, we're in this area. Again, ask yourself, did a new charge get introduced? Yeah, it did. This one is baselined at A, but now we've introduced a new charge that is baselined at B. Okay, what charge density was that though? Because now we have to include Q enclosed. So I'll show you what I end up doing is, because it's a sphere, this will always be true. But now the Q enclosed changes. So we have something that's baselined, which is this, or I guess this value is baselined. So a to the sixth over 6r squared will always be baselined there. But now we've introduced a new row. I called it x, o, ds. Or I guess we need to, well, yeah, ds, surface integral, because this is the same thing as q enclosed whenever r is between b and c, or I guess when r is greater than b, right? Or r at b, sorry, r at b. So now we've introduced a new charge density. And yes, we can take the integral because essentially it's always correct. But one thing that might come up is, you have a surface. How are you going to, like, how are you going to do this? What are the bounds going to be for this? This might come up often, and you might get confused. Are you going to use theta? Are you going to use phi? Because r will be, of course, 0 to b, or 0, 0 to b. But now you have a decision. Do you want to use theta or do you want to use phi? And that might get a little confusing. What I would do is, since it is a spherical, it is a surface charge density that is essentially constant, right? Because we have a 0 there. What you're going to do, or what you can do, is you can use this equation. Since it is a uniform charge density, and I'm only assuming this because it has this O. The only time he puts an O is whenever it's uniform, meaning it's a number. So what I'm going to do is I'm going to say, okay, rho xo is going to be equal to the charge that that surface has divided by the surface area. Okay. So then what happens? This is the same thing as doing the integral, by the way. So you don't have to technically like do all this work, but this is going to be the same thing. The charge is what we're looking for, so we can say the charge, or Q enclosed at B, is going to be equal to what? Rho x0 times the surface area of a sphere, which is 4 pi r squared. Now, be careful because remember, this is not r. What is it baselined at? It's baselined at B. So you're going to use B squared. That's where the charge lies. It does not change. It is not a variable. That is the spot the charge is at. So now what we have is we have a complete equation for the enclosed charge. A to the sixth, 6r squared, plus, oh wait, hold on. No. This is just a to the sixth over 6. dr 4 pi r squared. The q enclosed is just a to the sixth over 6. This only happens when you divide by 4 pi a to the sixth. I missed that. Yeah. So it's here, 4 pi a to the sixth over 6. That's the q enclosed between a and b, or that charge density. So now what do we have? Well, we have rho x0 4 pi b squared. And now we can divide by 4 pi r squared. And what do we get? Well, we get dr is equal to, well, it looks like we can factor out at 1 over r squared and keep a to the sixth over 6 because the 4 pi's cancel here, right? And we get plus rho x0b squared. Now, when we change it into the electric field vector, you remember you divide by epsilon naught, we can now put that on the outside. 1 over epsilon naught r squared times a to the sixth over 6 plus rho x0b, not rho, b squared. And that is our answer. Again, don't forget it's projecting radially. Don't forget that unit vector. B to C, perfect. We've done B to C now. Hopefully this made sense. There aren't too many steps to this, but the underlying principle needs to be there. You have to know the knowledge and the background to be able to do this. Now, from what is next? We've done B to C. So C to D we've already done. Remember, it's 0 because we're inside of a PEC shell. Now, R greater than D. Now, this one is actually going to be kind of easy, mostly because it's going to be the same as B is less than R is less than C, the one we just did. Well, why is that? Well, the perfect electrical conducting shell, I believe that's what it is, the PEC shell doesn't change the it doesn't change the electric field vector. Well, what does it do? what does the PEC shell do? This will go into, we'll talk about this more in the next video, actually, because part B, C, and D, or I guess C and D, all have problems, or this is the answer to them. But remember, this projects radially outwards, right? So, or the charges project radially outwards. So if we do this, the perfect electrical conducting shell does not change the electric field. What it does is it does not have any change on the inside, right? So now, what do we notice? Well, the electric field in here is going negative, right? Because it's going in. So it's negative on the inside. But it must be the same on the outside. This means it must be positive on the outside, right? Because there's no change in between. This is a Faraday's cage. Think about it. Nothing on the inside. This is all zeros, right? There are zeros there. The negative charge will be stuck on the inside because it's going in. Remember, if you have a surface that is drawing in charges like a pole, a magnetic pole, this will be negatives. Then, what else happens? Well, we have a positive coming out on the other end. And these are, of course, positives. Going out is positive, going in is negative into a surface. A PEC shell has 0 electric field on the inside. So everything that goes in must come out. Now, when R is greater than D, what we're going to get is the same as B is less than R is less than C. So, I mean, you don't have to do anything. Nothing's different because we've baselined that charge to be at B and baseline the charge to be at A. So we don't have to change anything. There's no change in anything. So whenever the radius is greater than D, what we have is, of course, the same thing. And that is actually the end of this video, because that's pretty much all I'm going to do. I'm not going to make this video like 40 minutes long. No reason for it. I'll just do the rest later and show you how to do that. But this is definitely going to be a problem. I mean, PEC shell is very important. You have to know what that means. This introducing charge densities and solving for electric field is very important. We have to know how it works. This is going to be a problem. I assume this is going to be like the sort of problem we're going to see like every single question, part A, part B, part C, and part D, because if they asked in the homework, you should know how to do this now. If you don't, it's totally fine. Just make sure and study it. Watch these videos. Do whatever you can to make sure you're prepared for it. Anyways, hopefully this helped. If you have any questions, please reach out to me, comment. But yeah, thank you all.